For the last 100 years or so, our power grid has been a pretty simple, predictable one-way street. But that's all changing. There is a literal tsunami of new energy sources crashing into that old system. So today, we're going to dive into the incredible smart technology that's being built right now to tame that wave and keep our energy future secure.
And really, that's the big question, isn't it? We have millions of new solar panels, wind turbines, electric vehicles, all trying to connect to a grid that's, well, a century old. This system was never ever designed for power to flow two ways. Now, this is a massive challenge for sure, but it's also an absolutely incredible opportunity.
Okay, so before we can get to the really cool solutions, we first have to wrap our heads around the core problem. And it all boils down to this fundamental shift in how we make and use electricity.
This quote from a PhD thesis, it just nails it. Bringing in all this renewable energy and what experts call distributed energy resources, that's just a fancy term for things like your rooftop solar or a home battery, it's causing some serious headaches for grid operators. See, unlike an old coal plant that just hums along providing steady power, these new sources, they're all over the place, and that creates instability.
And here's the difference in a nutshell. We are moving from the old grid, a simple top-down system, to the new grid, which is this incredibly complex, decentralized web. The sun doesn't always shine, the wind doesn't always blow, and now power is flowing both to our homes and from our homes. This constant fluctuation can cause some really dangerous dips and spikes that our old grid just wasn't built to handle. So how in the world do you manage millions of tiny, unpredictable power sources? Well, the short answer is, you don't. Instead, you get them to manage themselves by bundling them all together into something way bigger and way smarter, a virtual power plant.
A VPP is basically a power plant made of software. It has no smokestack, no turbine, nothing like that. Instead, it's a cloud-based system that uses super sophisticated algorithms to pool together thousands of those distributed energy resources, all those solar panels and batteries, and gets them to act like one single, giant, predictable power plant. It's pretty genius.
I love this analogy. Think of it like an orchestra of electricity. The VPP is the conductor, right? And the instruments are everything from the solar panels on your roof, the home battery in your garage, to your smart thermostats, and even your electric car plugged in overnight. The VPP can ask thousands of EVs to pause charging for just a few minutes, or tell thousands of batteries to push power back to the grid, all at the same time in perfect harmony. But, an orchestra this huge and this complex needs more than just a conductor. It needs a whole new set of brains, a mission control really, to manage the entire symphony and make sure that power gets exactly where it needs to go, safely and reliably, every single second.
To manage all this, we have two key systems, ADMS and DERMS. Let's stick with an analogy. Think of the grid like a city's road network. The ADMS, that's the Advanced Distribution Management System, is like the air traffic control for the major highways. It's looking at the big picture, managing the huge transmission lines to make sure the whole system is reliable. The DERMS, the Distributed Energy Resource Management System, that's your local traffic control. It's managing the millions of smaller neighborhood streets, coordinating all those devices behind the meter, like your home solar panels and EV charger.
So here is the absolutely crucial part. These systems can't work alone in their own little silos. A DERMS can't just tell a million electric vehicles to start charging all at once without the ADMS knowing about it and making sure the highways can handle that massive load. They have to be constantly talking, sharing data, and coordinating their actions. They have to operate as a fully integrated system of systems.
Okay, so we've got the orchestra, that's our VPP, and we have the brains, the ADMS and DERMS. But how do they all talk to each other? How does a utility server made by one company talk to a home battery made by a totally different company?
And that right there is a huge challenge. Without a common communication standard, you just have digital chaos. It'd be like trying to run the United Nations without any translators. It just wouldn't work. But thankfully, a universal language for the grid is emerging. That language is a technical standard called IEEE 2030.5. And what that really is, it's a protocol, a set of rules that allows the utility's main server to speak directly to an individual device, like your EV charger or your home battery. It gives it simple commands to help balance the grid. Now, the other way this works is through an aggregator, and that's our virtual power plant again. In this model, the utility only has to send one message to the VPP. The VPP then acts as that middleman, translating that single command and sending it out to the thousands of different devices it controls.
That IEEE 2030.5 standard is the universal translator that makes this whole conversation possible. All right, let's put it all together. Let's see how all these pieces, the VP, the DRMS, and this universal language, come together in a real-world, high-stakes situation to, prevent a blackout. So imagine a huge power plant suddenly trips and goes offline. The grid's frequency, it's like its heartbeat, starts to drop, and that's really dangerous. The DRIMS instantly detects this, and using that universal language, flashes an emergency signal to the VPP. The VPP immediately commands thousands of home batteries to inject power back onto the grid. And the result? The entire grid is stabilized. And the most incredible part is the speed. This whole process from crisis to resolution can happen in 2 seconds, sometimes even less. It's just amazing.
And hey, this isn't just theory. This diagram here shows the actual data from a real-world test of this communication protocol. Now, you don't need to follow every single step. The key takeaway here is that this is a real automated conversation happening between the grid and a device. The command is sent, the action is taken, and the result is confirmed back to the mothership. It actually works.
And this brings us to what might be the most important part of this entire transformation. Because this isn't just about giant utilities and cool tech companies. It's about you.
Think about it. For 100 years, we've been passive consumers of electricity. We flip a switch and the power is just there. We don't think about it. But that is fundamentally changing. With smart thermostats, home batteries, and electric vehicles, our homes are becoming active, participating members of the grid. We're no longer just part of the demand, we are now part of the supply. So the real question we all need to start asking ourselves is this: what role will we play when our homes become the power plants of the future?